Welcome to this Filipino engineer learning video on transmission line parameters and models. In 5 minutes, we will connect the resistance, inductance, capacitance, and conductance of an overhead line to the short, medium, and long line models used in power system studies. By the end, you should be able to interpret the distributed or LCG model, select an appropriate line representation, and read the principal outputs from 3 consistent worked examples. The examples use per phase ABCD constants for a balanced, fully transposed 3-phase overhead line. A uniform line is described by 4 quantities per unit length. Series resistance is R. Series inductance is L'. Shunt capacitance is C'. Shunt conductance is G. These form the series impedance Z equals R plus J omega L', and the shunt admittance Y equals G plus J omega C'. Omega is 2 pi F. Start resistance with the direct current value, correct it for operating temperature, then apply a conductor-specific alternating current factor. For inductance, calculate geometric mean distance and use conductor geometric mean radius, not physical radius. For capacitance, use the physical equivalent radius. Shunt conductance represents leakage and related real loss, but is normally very small for overhead line load flow models. A common 50 Hz convention classifies short lines below roughly 80 kilometers, medium lines from roughly 80 to 250 kilometers, and long lines above roughly 250 kilometers. A short model keeps total series impedance and neglects shunt admittance. A medium model uses the nominal pi. A long model uses continuously distributed parameters. Required accuracy and gamma times length remain the deciding criteria. All 3 examples use the same illustrative conductor and geometry. The equivalent phase spacing is 5.0397 meters. At 75 degrees Celsius, the alternating current resistance is 0.10066 ohms per kilometer. Reactance is 0.38110 ohms per kilometer, and susceptance is 3.00452 microsiemens per kilometer. The short line case is 50 kilometers at 132 kilovolts, supplying 100 megawatts at 0.9 power factor lagging. The shunt branch is omitted. The calculated sending voltage is 143.358 kilovolts line to line. Sending and receiving current are 485.985 amperes. Efficiency is 96.56%, and regulation is 8.60%. The medium line case is 150 kilometers at 220 kilovolts with the same load. The nominal pi model places half the total shunt admittance at each end. The calculated sending voltage is 237.770 kilovolts line to line, and sending current is 268.075 amperes. Efficiency is 96.56%, and regulation is 9.49%. The long line case is 300 kilometers at 400 kilovolts. Exact hyperbolic equations define the ABCD constants. The calculated sending voltage is 401.587 kilovolts line to line, and sending current is 195.995 amperes. Efficiency is 97.78%, and regulation is 5.79%. The negative sending reactive power in this example indicates net capacitive export toward the source. Before using any model for design, replace illustrative data with manufacturer values and survey geometry. Calculate positive and zero sequence parameters separately. Check reciprocity using AD minus BC equals 1 and reconcile real loss with 3I²R. These examples are instructional, not construction values, and a qualified power system engineer should review the final study model.